Chapter 4, Lesson 3 is all about the behavior of fluids as we continue our study of matter. I'm on page 116 in my textbook, and on the left-hand side in the What You Learn section, students will explain why some things float but other things sink, and students will describe how pressure is transmitted through fluids. Let's jump into it. Pressure. It's a beautiful summer day when you and your friends go outside to play volleyball. Much like the kids in figure 15, there's only one problem. The ball is flat. You pump air into it until the ball is firm. The firmness of the ball is the result of the motion of the air particles in the ball. As the air particles in the ball move, they collide with one another and with the inside walls of the ball. As each particle collides with the inside walls, it exerts a force pushing the surface of the ball outward. A force is a push or a pull. The forces of all the individual particles add together to make up the pressure of the air. Pressure is equal to the force exerted on the surface divided by the total area over which that force is exerted. Our equation for pressure equals force over area, or force divided by area. When force is measured in newtons and area is measured in square meters, pressure is measured in newtons per square meter. The unit of pressure is called a pascal, PA. A more useful unit when discussing atmospheric pressure is the kilopascal, which is 1,000 pascals. Force and area. You can see from the equation on the opposite page that pressure depends on the quantity of force exerted and the area over which that force is exerted. As the force increases over a given area, pressure increases. If the force decreases, the pressure will decrease. However, if the area changes, the same amount of force can result in different pressure. Figure 16 shows that if the force of the ballerina's weight is exerted over a small area, the pressure increases. If that same force is exerted over a large area, the pressure will decrease. For example, if you try and stand on the bottom of your feet, it's probably a lot easier than it is to stand on your toes. That's why ballerinas have to wear these specially shaped toes that allows them to arch their foot up and they can stand on that small area. If they're standing on that small area, that pressure is going to be exponentially greater because the area is smaller and the amount of pressure or the amount of force is still the same based on that person's gravity. For example, you've got basketball shoes, and on the bottom of those basketball shoes, you've got tons of little lines that increase the surface area on that shoe. Well, what does that do? That increases the ability to stick to the floor. So you've got a larger area, therefore there can be the greatest amount of force or stickiness so you're not slipping and sliding all over the basketball floor while you're playing the game. If you've ever walked through snow that's really deep, it can be really difficult. That's probably because the area for your feet is relatively small and your weight is greater than the force of that snow being packed together that you break through and fall into the snow. Well, how do people get over that or beat that? They wear snowshoes. This increases the overall area, which therefore decreases the pressure, and then they stay nice and light and they float right on top of the snow as they're walking through it. Let's complete this little activity that will hopefully help us to focus us on this difference between pressure and area. Complete the form for pressure, then analyze how pressure changes with a change in force or area. Pressure equals force over area, or force divided by area. If a force increases and area stays the same, pressure increases. Pressure and force are directly related to each other. If a force decreases and area stays the same, then the pressure will decrease. If force stays the same and the area increases, pressure decreases. That's the example that uses the snowshoe. If the weight that you have is the same and the area increases, you've got a snowshoe now, you're not going to break through, your pressure decreases. If the force stays the same and the area increases, you go up on your tippy toes, that pressure is going to increase and becomes really uncomfortable. Hence why ballerinas have to practice that for years and years to master the ability to stand on their tippy toes for extended period of times and move in those elegant ways. We continue reading. Atmospheric pressure. You can see it and you usually can't feel it, but the air around you presses on you with tremendous force. The pressure of air is also known as atmospheric pressure because air makes up the atmosphere around Earth. Atmospheric pressure is 101.3 kilopascals at sea level. This means that air exerts a force of about 101,000 newtons on every square meter it touches. This is approximately equal to the weight of a large truck. It might be difficult to think of air as having pressure when you don't notice it. However, you often take advantage of air pressure without even realizing it. Air pressure, for example, enables you to drink from a straw. When you first suck on a straw, you remove the air from it. as you can see in figure 17. Air pressure pushes down on the liquid in your glass, then forces liquid up into the straw. If you tried to drink through a straw inserted into a sealed airtight container, you would not have any success because the air would not be able to push down on the surface of the drink. In order for you to be able to drink out of something, you've got to let air go into that object. That air pressure is what is going to allow that flow to happen. That's the same thing as atmospheric pressure when you're drinking out of a straw. Balance pressure. If air is so forceful, why don't you feel it? The reason that pressure exerted outward by the fluids in your body balances the pressure exerted by the atmosphere on the surface of your body. Look at figure 18. The atmosphere exerts a pressure on the surface of the dancer's body. She is not crushed by this pressure because the fluids in her body exert a pressure that balances atmospheric pressure. So pressure is balanced because we've got fluids inside of us, and the fluids inside of us push on the fluid of air on the outside, and they balance each other out. Variations in atmospheric pressure on page 118. Atmospheric pressure changes with altitude. Altitude is the height above sea level. As altitude increases, atmospheric pressure decreases. This is because fewer air particles are found in a given volume. Fewer particles have fewer collisions and therefore exert less pressure. This idea was tested in the 17th century by a French physician named Blaise Pascal. He designed an experiment in which he filled a balloon only partially with air. Then he had the balloons carried to the top of a mountain. Figure 19 shows that as Pascal predicted, the balloon expanded while being carried up the mountain. Although the amount of air inside the balloon stayed the same, the air pressure pushing on it from the outside decreased. Consequently, the particles of the air of the balloon were able to spread out further. So as altitude increases, air pressure decreases. There's a direct relationship. As you're going up higher, the amount of air pressure decreases. So the balloon was actually expanding even though no other air was put inside of it. It was just less pressure on the outside of the balloon, so it got bigger and bigger and bigger. This is one of the reasons why planes choose to travel at those high altitudes, because there's less air pressure, therefore there's less resistance for them to fly. Air travel at the top of the page. If you travel to higher altitudes, perhaps flying in an airplane or driving up a mountain, you might feel a popping sensation in your ears. As the air pressure drops, the air pressure in your ear becomes greater than the air pressure outside your body. The release of some of the air trapped inside your ears is heard as a pop. Airplanes are pressurized so that air pressure within the cabin does not change dramatically throughout the course of flight, even though you feel this. Now, one of the ways in which Mr. Shane has experienced this is, one, on an airplane. A lot of times you're going to chew gum on your way up in your elevation because that'll allow that air pressure that's inside your ear to adjust. And I've also experienced it when I've actually dove down underwater learning how to scuba dive. I'm certified to go down to 50 meters, which is like 100 yards, about the length of a football field underwater. And as you go further and further and further, the pressure builds up and builds up and builds up on you to where you have to constantly be putting air from your nose back into the rest of your kind of sinuses by kind of plugging your nose, plugging your mouth, and then trying to exalt or exhale air into those sinuses to fill up. Otherwise, that air pressure is constantly pushing down and it kind of hurts you. As you're going higher in elevation, that air pressure is expanding and you feel that popping sensation. As altitude increases, pressure diminishes as the weight of the air column decreases. On average, with every 1,000 feet of altitude increase, the atmospheric pressure decreases by 1 inch of mercury, so one of those units every 1,000 feet up. If you go up in an airplane, you're flying from anywhere between 30 and 40,000 feet, so that's quite a bit of pressure that's changing, hence why you feel that pop in your ears. Changes in gas pressure on 119. In the same way that atmospheric pressure can vary as conditions change, the pressure of gases in confirmed or confined containers also can change. The pressure of a gas in a closed container changes with volume and temperature. Pressure and volume. If you squeeze a portion of a filled balloon, the remaining portion of the balloon becomes more firm. By squeezing it, you decrease the volume of the balloon, forcing the same number of gas particles into a smaller space. As a result, the particles collide with the walls more often, thereby producing greater pressure. This is true as long as the temperature of the gas remains the same. You can see the change in the motion of the particles in figure 20. What will happen if the volume of the gas increases? If you make the container larger without changing its temperature, the gas particles will collide less often and thereby produce a lower pressure. Pressure and temperature. When the volume of a confined gas remains the same, the pressure can change as the temperature of the gas changes. You have learned the temperature rises as the kinetic energy of the particles in a substance increases. The greater the kinetic energy is, the faster the particles move. The faster the speed of the particles is, the more they collide and the greater the pressure is. If the temperature of a confined gas increases, the pressure of the gas will increase, as shown in figure 21. Our reading progress check says, why would a sealed container of air be crushed after being frozen? Well, if you decrease temperature, that pressure is going to decrease. As you increase temperature, that pressure is going to increase because that air expands. Let's take a look and review that relationship between these two items. Pressure increases as volume decreases. So if the amount of area that something is in, the amount of space that it's in is decreased, that pressure increases. Here's how we use an air compressor. An air compressor pumps air into a smaller space, and then the air is let out of that air compressor for specific types of kind of tools and activities. So to pump up a tire, an air compressor will pump itself up and have this increased pressure, and then you're going to put that into the tire, which then obviously being flat or into a ball that's being flat will increase the overall pressure inside of that item, either the tire or the ball. Pressure increases also as temperature increases, because temperature increase is going to activate those particles and they're going to move faster. More of those collisions have them expanding and filling up that container. If something gets colder, like if you leave a basketball or a football, something that's pumped up, you leave it outside when it's really, really cold, the next time you're going to come play with it, I bet you it's decreased and it's lost its overall air and actually goes into a smaller amount of space. So pressure increases as volume decreases. Pressure increases as temperature increases. Float or sink. You may have noticed that you feel lighter in water than you do when you climb out of it. While you are underwater, you experience water pressure pushing on you in all directions. Just as air pressure increases as you walk down a mountain, water pressure increases as you swim deeper in water. Water pressure increases with depth. As a result, the pressure pushing up on the bottom of the object is greater than the pressure pushing down on it because the bottom of the object is deeper than the top. The difference in pressure results in an upward force on an object immersed in a fluid, as shown in figure 22. This force is known as the buoyant force. If the buoyant force is equal to the weight of an object, the object will float. If the buoyant force is less than the weight of the object will sink. Objects that have a greater buoyant force than the force of that water will allow it to float. Objects that have a lesser buoyant force than the force of that water being pushed on it will sink, depending on the material that an object is made up of, and as we're going to learn, its density, that object will probably float or sink as well. Archimedes' principle, top of page 121. Archimedes' principle is defined as the buoyant force on an object is equal to the weight of the fluid displaced by the object. So when something is in water, it moves that fluid out of the way. Just like when you're in air, you move that fluid out of the way. Archimedes' principle says that the force of buoyancy, the force pushing on you that might cause you to float, is equal to the amount of water that's pushed out of the way. Now, we're going to pause the video right here, and I want you to click on this external link to watch the TED Talk educational video on how this was discovered, because it's going to show you how this operates and how this works to be used as a scientific principle, the Archimedes principle. Top of page 121. Archimedes' principle. What determines the buoyant force? According to Archimedes' principle, the buoyant force of an object is equal to the weight of the fluid displaced by the object. In other words, if you place an object in a beaker that is already filled to the brim with water, some water will spill out of the beaker, as in figure 23. If you weigh the spilled water, you will find the buoyant force on that object. It should weigh the same amount as the object itself in the water because it's moving that much water outside of it. Density. Understanding density can help you predict whether an object will float or sink. Density is mass divided by volume. An object will float in a fluid that is more dense than itself, and sink in a fluid that is less dense than itself. If an object has the same density, the object will neither sink nor float, but instead stay at the same level in the fluid. An object will float in a fluid that is denser than the object. So if something is less dense than water, it will float. Something is less dense than water, it'll float. Hence why a life vest is made out of kind of styrofoam material. A air vest or the floaties are filled with air, or tubes are filled with air. Those are less dense than the fluid water itself. That's why they float on the top surface of the water. In letter B here, it says an object with the same density as the fluid will stay at the same level in the fluid. Here's what you try to do when you're scuba diving. Humans have fluid inside of them and the water outside of them kind of balances out, but you're carrying an air tank on you which has less density than the water itself, so it kind of makes you float. You've got to find a way in which you can let air out of your suit itself that'll allow you to sink, and then you kind of regulate by being suspended in the water because you don't want to be sinking and floating and sinking and floating. You want to be able to swim just like the fish, who have a way in which they regulate that as well. An object will sink in a fluid that is less dense than the object. Object will sink in a fluid that is less dense. So if the liquid is less dense and the object is more dense, it'll sink. How is it possible then to have these huge, massive metal tanker ships? Metal is more dense than water. And how do these then float on water? Well, why can a boat that is made out of materials that are more dense than water float? Should be impossible, right? The hull of the ship actually displaces more water than the weight of the boat. So this big, huge bottom part that's pushing on the water, it actually pushes more water away, and the weight of that water is greater than all of the weight that's on this actual ship itself. According to Archimedes' principle, if the buoyant force is greater than the weight of the object will float. So the force of the liquid being pushed away is that buoyant force. Therefore, the force being pushed on the bottom of the ship is greater than the actual weight of the ship pushing down. It then has this miracle aspect of floating. The next principle we have is Pascal's principle on page 122. What happens if you squeeze a plastic container filled with water? The container is closed, the water has nowhere to go. As a result, the pressure in the water increases by the same amount everywhere in the container, not just where you squeeze or near the top of the container. When a force is applied to a confined liquid, an increase in pressure is transmitted equally to all parts of the fluid. This relationship is known as Pascal's principle. Hydraulic systems. You witness Pascal's principle when a car is lifted up to have its oil changed, or if you are a dentist chair, as it's raised or lowered, as shown in figure 24. These devices, known as hydraulic systems, use Pascal's principle to increase force. Look at the tube in figure 25. The force applied to the piston on the left increases with the pressure within the fluid. That increase in pressure is transmitted to the piston on the right. Recall that pressure is equal to the force divided by area. You can solve for force by multiplying pressure by area. Pressure equals force times area, or force equals pressure times area. If two pistons on the tube have the same area, the force will be the same on both pistons. If, however, the piston on the right has a greater surface area than the piston on the left, the resulting force will be greater. The same pressure multiplied by a larger area equals a greater force. Hydraulic systems enable people to lift heavy objects using relatively small forces, because the same force is applied throughout the fluid or throughout the liquid. So when that liquid area is greater, that same force spreads out over that entire area, which allows hydraulics to pick up really, really heavy things with a small amount of force that's being provided. An example of a force pump, similar to the hydraulic system, is that of your heart that's depicted on the top of page 123, force pumps. If an otherwise closed container has a hole in it, any fluid in the container will be pushed out at the opening when you squeeze it. This arrangement, known as a force pump, makes it possible for you to squeeze toothpaste out of the tube or mustard from a plastic container. Your heart has two force pumps. One force pump pushes blood to the lungs where it picks up oxygen. The other force pump pushes the oxygen-rich blood to the rest of your body. These pumps are shown in figure 26. So a force pump is an example of a hydraulic system, but it's in a more simplified version when it's coming to you brushing your teeth or kind of squeezing something to get something out of it. Your heart is an example of this, but it's pushing blood to and from the different parts of your body. That's all we have for lesson 3. God's blessings on completing your notes and your behavior of fluids reinforcement.